Hello, today I will do a presentation about the paper Attributed Network Embedding for Learning in a Dynamic Environment. Network embedding leverages node proximity manifested to learn a low-dimensional node vector representation for each node in the network. Given a graph G, where each node is associated with a set of attributes, attributed network embedding maps each node V to a compact vector, which can be used in downstream machine learning tasks. A vast majority of existing attributed network embedding methods have a fundamental assumption that networks are static. However, in reality, network structure often evolves over time with addition, deletion of links and nodes. In this paper, authors tackle this problem by proposing a novel dynamic attribute network embedding framework, DANE. There are two major challenges. The first is inherently correlated network and node attributes could be noisy and incomplete. It necessitates a robust consensus representation to capture their individual properties and correlations. To solve this problem, authors designed an offline model to reduce the noise of raw data representations and then embed the network. And the second challenge is the embedding learning needs to be performed in an online fashion to adapt to the changes accordingly. It is time consuming to train an offline model at each time step. Others built an efficient online embedding algorithm, which gives an informative embedding representation on the fly. The pioneer of network embedding can be dated back to the 2000s. The method target to build an affinity matrix that preserves the local geometry structure of the data manifold and then embed the data to a low-dimensional representation. However, these methods are limited to deal with plane networks. In many cases, we are often faced with attributed networks. And also, many efforts have been devoted to gain insights from attributed networks. Some of them are based on factorization, and some of them are based on deep neural networks. Nevertheless, all these methods can only handle static networks. It is still not clear how to learn embedding representations efficiently when networks are constantly evolving over time. Therefore, this paper is the first paper about the attributed network embedding in dynamic environments. Here is the structure of the model. The upper side is the offline part, and the lower side is the online part. According to spectral theory, by mapping each node in the network to a k-dimensional embedded space, the noise in the network can be substantially reduced, and a rational choice of the embedding is to minimizing this loss, where yi and yj represent the corresponding embedded vector for node I and node j, and aij represents whether there is an edge between node I and node j. By minimizing this loss, it ensures that connected nodes are close to each other in the embedded space. In this case, the problem boils down to find the top k eigenvectors of Laplacian matrix of the network. Similarly, for attributes network, the task is to find the top k eigenvectors of cosine similarity matrix based on attribute matrix X, which is here. and then other projects and combine both embedding matrix yx and ya to get the final embedding representation y. Here, authors use factorization methods to compute embedding representations. I think, as I mentioned in my last presentation, we can use a random walk algorithm to deal with both nodes network and attributes network at the same time and get an affinity matrix directly, which will be more efficient and which is feasible to massive graphs. Here is the online part of the model. The core idea to enable online updates of the embeddings is to develop an efficient way to update the top K eigenvectors and eigenvalues. Otherwise, the algorithm has to perform generalized eigen decomposition which is the offline part at each time step, which is not practical due to its high time complexity. You can see in algorithm one, we need to calculate the changes of eigenvalues and eigenvectors, which is delta lambda I and delta A. Here, LA represents the Laplacian matrix of matrix A, and DA represents the diagonal matrix, where each diagonal entry is the summation of that row. And A represents the eigenvectors. We can easily calculate the changes of Laplacian matrix delta L and the changes of diagonal matrix delta D based on the original matrix. And we can substitute the changes into this formula to get the second equation. And after expanding this equation, authors ignored the higher ordered term as they have limited effect on the accuracy of the generalized eigensystems, which makes it easy and efficient to get delta lambda and delta A. This approximation is the most impressive part in the paper, which largely reduced the time complexity of the online part and make the online updates visible for large networks. Authors evaluated their model on the network clustering task and node classification task on 4 different data sets compared to 5 competitors. Note that here, DANE/A refers to the model trained only on attributes information, and DANE/N refers to the model trained only on network information. And DANE/O refers to rerun the offline part, which is the generalized eigen decomposition for every time step. And we can see here DANE/N does not perform well if we do not consider the attributes information, and if it gets a worse performance than deep work and line on both tasks. Therefore, if you got a planned network that does not contain the attributes information, I recommend you not to use DANE model. However, for the attributed network, in this graph, it's network plus attributes here. You can see that in both tasks, DANE/O achieves the best performance among all the models. Although like DANE is a little worse than DANE/O, it still beats all other competitors. This is reasonable since the online part of DANE model use approximate value for the updates instead of exact value, right? So it will slightly influence the results. Authors also evaluated the efficiency of the ANE model. This graph shows the cumulative training time for each model on 4 different data sets. You can see that DANE with online part, like online update part, is the black line in each subgraph, and it is at least 10 times faster at step 10, and it is sometimes 100 times faster than some model at step 10. And here it's 10 times faster here, yeah, 10 times faster here, and 10 times faster here. Yeah, this makes it feasible for some real-world application on large networks. And for small networks, if you really considering to achieve a good the best performance, I would recommend you to use the DANE/O, which is rerun the offline parts at each time step, since it has the best performance and the time complexity is lower than other models. Yeah, DANE opens up future researches in multiple directions. Firstly, while DANE excels in various tasks, it faces challenges when applied to massive graphs. To address this issue, we can implement the random walk algorithm from PANE, as featured in my last presentation, to enhance the efficiency of offline training. Secondly, considering DANE's two-fold structure, encompassing both an offline and an online component, there is potential to develop a distributed version of DANE. This distributed approach involves having the offline model on local devices and the online model residing in the cloud. Moreover, the concept of federated learning can be integrated into this distributed net framework. In practice, to safeguard data privacy, user data sharing among different entities is not allowed. Instead, with the implementation of encryption techniques, diverse companies can collaborate on training an embedding model through a trusted third party. For example, local stores and local hospitals have some network data related with local people, and they want an embedding representation for the whole local network. They have their initial embeddings in their own devices, and every time there is a change in their network data, for example, a deletion or insertion of a node, they send the change to the cloud to do the online updates, and then update their local embeddings based on updates received from cloud. During this process, users' data is not shared, but the embeddings contains information from both stores network and hospitals network, which enhance the quality of embedding representations without sharing the data. Oh, that's all of my presentation. Thank you for watching.